In terms of resonance, okay, and wave problems, this is one of the trickier ones you'll do where you want to put it all together. Reads a guitar string of length 0.774 meters is fixed at both ends. It's a fixed end harmonic system. The string is plucked and a standing wave is set up so that it's vibrating at its third harmonic. The traveling waves that make up the standing wave have a speed of 178.1 meters. What is the frequency of vibration? Okay, most people are like, whatever, I don't care. Let me just play my guitar. I want it to be in tune, okay? But a good musician, a good guitarist, actually understands how this all works, what's called harmonics. In fact, on a guitar, the 12th fret, that's the only one I know off the top of my head, is exactly the middle of the string. So if you actually put your finger lightly on the 12th fret, you actually force a second harmonic. It's an octave higher. If you put it a third of the way on a guitar, I think it's the 7th fret, that'll force the third harmonic because you cut the string into 3 parts. And then it's actually 3 octaves higher than the original note. Okay? Whereas if you push your finger down all the way, you cut the length of the string down, but it actually won't be 3 octaves higher. You get a totally different sound. Okay? So a guitarist knows how harmonics work. In fact, if you take guitar lessons, your music teacher will use these terms. Let's set this. So before we set this all up, a little quick review. If you remember this simulation here, it looked at visualizing the harmonics on a string, okay? And the third harmonic is the third easiest way you can shake a fixed end system. And the way you visualize that is instead of 1 bump, remember we had the giant rubber band machine up here and all that? We sped it up. What's the third easiest way? You have how many bumps? How many antinodes? There are 3, exactly. That's what we want to visualize, okay? So, step 1, let's make a little what? Little sketch, okay? So here we have a guitar, which we don't really need to draw out because, I don't know, that's not the important part. Sure, I'll sketch out a guitar. There you go. Ooh, that's a guitar, right? But the important thing is drawing the string, okay? And in this case, it's the third harmonic. So instead of 1 bump, instead of 2 bumps, how many bumps? 3 bumps. 3 antinodes is what we're trying to sketch out, okay? And again, what's hard about drawing it on a piece of paper is you have to remember that waves are alive, they're moving, they got energy, which is why it's nice to use computer simulations and visualizations to picture it, okay? The third harmonic has a node, antinode, node, antinode, node, antinode, node. Holy cow, a nan, 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 okay? There was an old cheesy TV show with Adam West. It was Batman and Robin, and I don't know if you've ever seen it. It's really hokey, like bam, poof. It's got like the Joker and all that. And the theme song is totally lame. You could tell they just paid some guy $10 to write the song because the lyrics go na 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 Batman, and then the second verse is na 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 Batman. Okay, so whatever, right? So that's actually kind of a trick. You can remember how many wavelengths are here by looking at how many nan-nans there are. Okay. That was kind of bizarre, but maybe that'll help you, okay? For every node, antinode, node, antinode, node, this is 1 wavelength, okay? A nan-nan. So every node, antinode is just a quarter of a wavelength. So how many wavelengths are here? Let's count, right? To repeat yourself. So this is going to be how many wavelengths here? This is 1 node, antinode, node is half a wavelength. This is another half, right? So how many do we have altogether? Inside the length of the string is 3 halves of a wavelength, or 1.5 wavelengths. You see that? Therefore, the wavelength is equal to what? 2/3 the length of that string there. That's the key, is you need to find the wavelength before you can then find the velocity and all that good stuff. Okay? So that good question is, why is it 2/3 the length? If it's 1.5 wavelengths here, then the way to solve for wavelength is you divide both sides by 1.5, which is the same as multiplying by the reciprocal of 2/3. Okay? Next, step 2, list all the what? Knowns and unknowns. Okay? So in this problem, let's take a look at numbers we're given were 0.774 meters. So that's our first number, is the length of the string. 0.774 meters is the length. So right away we can find the what? We can find the wavelength, right? By taking 0.774 and multiplying that by 2/3, right? Or divided by 1.5, same thing. And it's 0.516 meters, okay? Next, we can look at our other information given. The other information given was the velocity of the sound in the string is 178.1, and we're trying to find frequency. Okay, so V is 178.1. and we're trying to find frequency. So now it's a pretty trivial problem because there's only one equation, and it's a big one that we use all the time, that relates velocity, wavelength, and frequency. V equals lambda f, okay? The speed of a wave depends on its size, its wavelength, the distance it takes to repeat itself, and then how quickly the wave can regenerate itself, okay? One interesting example of that was Usain Bolt when he was setting on these records. Scientists were trying to analyze what's the human limit, and one set of sports scientists actually looked at him kind of like a wave in terms of how big his stride is and how quickly, the frequency of how quickly he can regenerate his stride for a sprinter there, right? So anyway, let's just plug and chug. So now in step 4, literally we just plug in all our numbers, okay? And notice this is kind of like a little jigsaw puzzle where you're trying to piece it all together. But it's a nerdy jigsaw puzzle. So the 4 steps gives you a process to break it down. So even if you don't even know what the problem is about, you can kind of look at it visually. It's about a guitar. There's a string vibrating. Looks like it's got 3 bumps, third harmonic. We know the length of the string. We know the velocity. We're finding the frequency. Velocity is 178.1. Lambda is 0.516. Solve for frequency. So all I got to do is simply take my calculator and take 178.1 divided by 0.516, okay? And survey says, when we punch that all in, we take 178.1, we divide it by 0.516, there we go, and we get a final frequency of 345.155. Keep a couple decimals, okay? 344.155, good enough. Units would be 345, there we go, thank you. Fatigue is kicking in. There we go. Hertz. Okay? So to summarize, let's take a look at this really quick, right? All we do is we sketch out our waveform. Based on the length of the string, we can find the wavelength. There is 2/3 of the wave present in that string. Therefore, if we use V equals lambda f, we plug it, we get our final frequency. This is the hardest one because it ties it all together. Okay?